Okay, so let's go through this example. So we're applying vectors. Now, a lot of this is dealing with distance and time. That's why I've said this. So this example is to do with boats travelling on water. So boats have two-dimensional travel. They travel along the surface of the water. They have an x component and a y component to their direction. I guess you could say north, south, east, west, whatever. But they follow a path which we can describe that as a straight line, and therefore we can explain their movement in terms of the vector equation of a line. Right? If it was an aircraft, potentially you would change the situation from 2 dimensions to 3 dimensions. So obviously a plane can move up and down as well as left and right. Okay. I guess straight lines, it's an approximation to travel, but it's fine, it's what we're working on. So, typical question, this one we're going to go through as an example. Just got to understand really, when we say application of vectors, I'm not giving you any new skills, it's just about applying it to a certain situation. So we're saying that position vector of a boat t hours after it leaves a harbour is given by, so R1 equals, now I'm going to add something in here, just maybe to help you keep things consistent, right? It says position vector is given by t is t times 30:15. Now that means with every hour it travels 30 kilometres in an x component and 15 kilometres in the y component. Now we are used to seeing something in front of that, which is the initial point, starting point. So what could you include before that? It's not necessary, but so we say the position vector of the boat is given by t 30:15. We could have included a 0, 0. Okay, so we could put a 0, 0. Right. Because, do you remember the equation of a line, a vector equation of a line? You start with a position vector of a point on the line, yeah, and then you work out the next part of it is the direction, and then the magnitude of how often you do it. Now, what we know about this first boat is that it leaves a harbour. So relative to the harbour, its starting point, we could say is 0, 0. Right? Now, the second boat, I'll call that R2, is given by 52 plus T 10, 10. Okay. Now, what do we know, Noah, about the second boat and its position? Sorry, if I got that right. 55, yeah, I'm reading it wrong. 55. What do I know about the position of the boat now?
That means you know where
Give me a definite statement, not that, oh, we know. I want, what do I know?
That starting point is 55.
Pardon?
That is,
And what does that mean?
That means that it's 50 kilometers somewhere.
Which basically means, where is it not?
It's not in the same place as the other.
Yeah, it's not in the same place as the other, and it's not at the harbour. It's already out in the sea somewhere. So we have a component now. If we understand that, then the first part of the question, how far apart are the boats at the time the first boat leaves the harbour? So basically, we're only interested in what? So pi, when the boat leaves the harbour, but just out of consistency, what would I use as t? T equals 0. Yeah, t is time. T is 0 when the first one leaves the harbour. That's the starting point. And that negates this second half of each line. So then we need to know how far apart are the boats. Well, this is the starting point. That's why I went through that. So we've got to find the difference between 0, 0 and 55. And how do we do that? So we're using Pythagoras' theorem. So we're basically saying that boat A is here and boat B is, and we're looking at 50 in the x direction and we're looking at 5 in the y direction. So to find the distance between the two, okay, we want the magnitude, don't we, of the difference between the position vectors. Now because we've got a 0, 0, now this question could change if both boats are out sailing around somewhere. So Pythagoras' theorem states that we have the square root of 50 squared plus 5 squared, which works out as 50.2 kilometres, looking at the example in the book. So what I want you to understand is how the components of the parts of the equations work here. Right? So in the question they didn't put a 0, 0 because they're trying to go, well, what do I compare it to? You know? So by you always thinking, well, there could be a 0, 0, that will help you. That will help you. Okay? Is that okay? So comparison of 2 points. Okay, next part then is how fast is each boat travelling? So, which part of the two equations is to deal with the travel? So the second part. So this bit here for both of them deals with how fast they're going. Now, we've got for boat A, we've got T 3015, and for boat B, we have T 1010. Now, what do we put as T? Doesn't really do it like this in their explanation, but, well, kind of does, but let's make a statement. What do we put T as if I want to know the speed of a boat? 1. Because speed is basically, but also you state a speed as how far it's travelled in, but more specifically, 1 unit of time. Yeah? 1 hour, 1 minute, 1 second. So this part of the equation of the line is actually the distance component, and therefore we want to know the distance within a particular amount of time. Alright? So what we do is we state T is 1 and then find the magnitude. Alright? So for instance, if it said how far does the boat travel in 3 hours, you'd have T is 3 and then find the magnitude. But by finding the magnitude when T is 1, we also get the speed. Okay? Alright, so when we work those out, so boat A, same thing again, 30 squared plus 15 squared, square rooted. We know T is 1, so we get the distance of 33.5 kilometres in 1 hour, so it's kilometres per hour, straight away. And boat B, the same thing. 10 squared plus 10 squared gives us an answer of 14.1 kilometres per hour. So it's that bit of understanding. That's so the line, the equation of the line is the initial starting point, and the second part is how far you travel given a certain time. Right? So if we do it in 1 hour, if T was in minutes, you'd get a speed in minutes per, however many meters per minute, that kind of thing. Make sense? Any questions on that? No? Okay. No question? Finally then, we've just got to work out, are the boats in danger of colliding if one of the boats does not change course? So what are we looking for again? The intersection of 2 points. So going back to the initial equations, we've got 30t should equal 50 plus 10t, and then we've got 15t should equal 5 plus 10t, and this, maybe you haven't come across this yet. If I now work out what t is, for this first one, we get t is 5 over 2. You're happy with, I'm not showing my working here, but you're happy that it's 5 over 2? Take 10t, you get 20t equals 50. Right, okay. And this one, you get t equals 1. Right? Now, in terms of this application, what does that mean?
You don't come to life.
Why though? Why does it mean they don't collide? Big, give me an answer in a real life, real term situation.
In order for them to get to the same point, it's a different amount of time, so that means by the time one gets there, the other
Okay,
one's
so
already
slightly different from what we were doing before. Will the boats ever take up the same position?
I mean, yes, but
Yes.
at a different time.
But at different times. Okay? So we're not saying in this case, when you've got 3 dimensions, there is a chance that they will never take up the same position. When there's only 2 dimensions, much more chance that they will actually hit that same point. Okay? There will be at some point. But we know that boat A takes 2.5 hours to get to that point, and boat B will get there in 1 hour. And then obviously they keep going, so there is no chance that they're going to hit.
How do we know that they will eventually be on the same point? I mean, that they both will be on the same point, but just in a different time. How do we know?
2 dimensions, are they going parallel to each other?
Yeah.
They're not going parallel, therefore they must cross at some point. Now, don't get too complicated with 2 dimensions. 2 dimensions, you remember you've only got 2 situations to deal with. Parallel or crossing. It's in 3 dimensions that they have skew, parallel and intersecting. Okay? So it's like aeroplanes. Would you want aeroplanes to ever be on this exactly the same point in the sky? Well, maybe within certain hours, but you would try to keep them completely apart from each other. Right? But when we've got boats on the water, they will hit the same point at some time, but it's just, is there enough time between for it not to worry about? Okay? So that's how we apply what we've been doing with vectors, with speed, and so on. Now, physicists amongst you, right? Those not, we obviously need to work on it. Potentially, the boat travel might change. How could we make a question much more complicated to do with boats travelling? 2 boats travelling, will they collide or not? What have we assumed in this situation?
That they have a constant speed.
Have a constant speed and,
Constant mass.
yeah, and what might change that vector? So you might have a boat travelling on, but what could change the actual...
Acceleration rate.
You're not really getting... Think, well, what happens on the sea?
The waves,
The water.
the places.
What do you say?
Water.
Currents. You ever had a problem in physics, guys, where you've got a boat travelling down a river or something, and you've got a cross current, or you want to cross a river, you've got the river current, and you get sent off. So you might head out on a certain vector, but your vector gets adjusted because of the current of the water. That's how a question could be made more difficult. So if you've got 2 boats, these are their vector equation line, but you might be asked to work out their actual vector equation of a line. And how would you work that out? So if you've got 1 boat now, and you've got the currents, what would you be looking at trying to work out?
How changes the speed.
No, I'm just thinking, how do you work out, what's it called? So you've got one vector, you've got another vector, you'd actually be looking for the, so you'd be looking for the, what's it called? When you've got one vector and another vector, you add them up because you are working out the what vector? The resultant vector. So you'd be making sure that you could work out the resultant vector. So let's say you were given two vector equations. You know, you need to be able to work out one effect on another. Okay? Anyway, so what do we need to do now? You need, in your time, not class time, to make sure you've been through all that vector stuff, okay, and finish this chapter with everything you need to know, make sure you understand it, make sure you can apply it. The exam style questions, make sure you do go through the application ones, definitely. Go through the review exercises, and that's it for us and vectors, unless I give you an exam questionnaire. Alright? So that means Wednesday, we'll then get on to our differentiation and integration of trig functions, alright, which may or may not take time. You never know, they might be done on Wednesday, and next week we can do revision, but you never know. But it is up to you to make sure you've got all this vector stuff done. So any questions on that we've just done, or what we did previous lesson? No? Okay, I'll let you get on there.